Hey, good morning. I'm going to go ahead and introduce us to glycolysis. But first, as an introduction, just remember that glycolysis is a cellular process that takes place within the cytoplasm. It does not take place within the mitochondria. The Krebs cycle takes place within the mitochondria, as does the electron transport chain. So if you think about it, all three of these processes are trying to give us ATP, which is for energy. But only these two happen in the mitochondria. The glycolysis process happens outside in the cytoplasm here. And what they're going to do is they're going to create ATP, but they're also going to give electrons to these carriers called NADH as well as FADH2. And if you see what glycolysis is doing, it's sending its electrons to the electron transport chain, and the Krebs cycle is doing the same. It's going to shower its electrons on there. But before we can understand much about this, we have to know, why do we have to transfer electrons? It has to do with a process called a redox reaction. So if I can introduce this really briefly here, a redox reaction involves the transfer of electrons and thus the transfer of energy. So if you think about an electron as a bundle of energy, when it gets transferred, it is transferring energy. And if you just saw down there, sodium had an electron and it gave it to fluorine. Sodium has thus lost an electron and fluorine has gained it. And in a way you could say sodium has lost energy, fluorine has gained energy. This is called a redox reaction or an oxidation-reduction reaction. Okay? One way that was helpful for me to memorize this was called oil rig. The oxidation of something means it has lost electrons. Oxidation is lost, whereas reduction is the gain of electrons. And in a way, oxidation is the loss of energy, and reduction is the gain of energy. So that's another thing to keep in mind here. And I know it's confusing because when you hear the word reduced, you always think it has less of something. But in this terms for chemistry, it's not going to be applying. Reduction actually means the loss of an oxidation number. But since we're not really going to talk oxidation numbers here, you do not need to know this for this course here. Just know that reduction is the gain of electrons and the gaining of energy, as fluorine just experienced there. Okay? So which element below is oxidized? Well, clearly the one that lost it was sodium, and the one that was reduced and gained energy was fluorine. On the other hand, which element is the oxidizing agent? Which element is causing the other to become oxidized? Which element is stripping the electron off of the other? If we watch this again, the one that is doing the stripping of electrons, it's fluorine. It's stealing the electron from sodium. Which element is the reducing agent? Which element is kindly giving that electron up? Maybe by force, but it's giving it up. It is sodium. So even though sodium became oxidized, it was a reducing agent because it was giving it up. If you think about it, this is not hard to understand, but it does take a little getting used to. And whenever you're stuck, just stop and think for a minute. Remember oil rig. It's all about where that electron is going. Okay? Now that we've talked about these electron transfers, look again back at this chart here. Hang on just a second. Now that we've talked about that, we'll go ahead and review this again. That glycolysis is going to give up electrons. It's going to cause NADH to become reduced, and therefore the products of glycolysis become oxidized. The electrons are going to go here, and the electrons are going to go and reduce the electron transport chain. The Krebs cycle is going to give up electrons, reduce NADH, and reduce FADH2, which will then come and give the electrons to the ETC, which will then become further reduced. So all of the energy is going up here and coming to the ETC. And that means the products of glycolysis are becoming oxidized. And as we go down the chain, glucose is going to become further and further oxidized. Okay? So in a nutshell, that is really what is happening through cell respiration. Now, what we're going to do is we're quickly going to take a look at glycolysis and how this entire process works. So, an overview of glycolysis. What we're doing is we're going to break down glucose. And when it splits in half, we're going to go down two distinct pathways. And at the end, we're going to be left with some ATP down here. I put in the boxes. And we're going to be left with 2 pyruvates. In the process of doing this, we are going to oxidize glucose and reduce NADH. That means this is going to have the energy, and we're going to strip the energy off of here and give it to NADH. And the glucose molecules are now going to become further oxidized. And really, that is all of cell respiration. As we go from the start, which is glucose, everything is going to start becoming oxidized. And as we go further down the chain, things get more and more oxidized. And so glucose has all the energy. It came from photosynthesis, and it came from the sunlight where all that energy was. But the energy is going to be stripped off and given to NADH, and pyruvate at the bottom here is going to have less energy. So we'll do this in a flow chart here to start with. The very first molecule in stage 1 of glycolysis is glucose. It has the most energy out there. In fact, just to kind of illustrate how much energy it has, let's just kind of have a little fun here for a moment. Shapes. I'm trying to find a fun shape here to work with, but I'm not very creative. We'll use the sun to signify there's a lot of energy there. Let me color it yellow for a bomb or fire effect. I'll push this up to the front. There we go. Here's glucose. Glucose has all the energy, and it came from photosynthesis. And with all that energy, we're going to strip the energy off of it and oxidize glucose. And we're going to turn this into fructose 1,6-biphosphate down here. Okay. First step, what we're going to do to destabilize this is we are going to add phosphates to it. Whenever we add phosphates to something, it's akin to seeing some small person walking through the hallway of school and putting books in their arm, a stack of books. They would obviously become destabilized, and they'd probably fall over or break their back really quickly. And that is exactly what's happening here. We're going to destabilize glucose by phosphorylating it. To do that, let's go ahead and draw a line here, a scribble tool line. We're going to go down here. Give my scribble tool line, which is really bad. Here's my arrow. I'm not sure where my arrow went, so I'm going to try that again real quick. Apparently it doesn't like me too much. I do not know what in the world is going on here. All right, we'll try this here. For some reason it likes this one a little bit better, and I'll improve the weight so it's a little bit bigger there. Maybe not too big. Okay. What we're going to do to phosphorylate it is we need to sacrifice some ATP to get a phosphate. And we're going to take an ATP right here, and we're going to strip a phosphate off of it and put it on there. Maybe I'll move it just a little lower, and we're going to do that one more time on this side. This is stage 1 to glycolysis. We are going to add a phosphate, and in the end we end up with ADP. We had to spend 2 ATPs to do this. So now fructose 1,6-biphosphate is phosphorylated, and it is destabilized. And that brings us to step 2. It's going to be so destabilized, it's going to want to split in half because it's simply not going to be stable enough to stay like this. Okay? So what we're going to do for the next one here is we're going to draw another arrow. Now, I'm not sure if this is going to work, but we'll see because the scribble tool didn't want to work last time. Okay, it worked there for some reason. Let's see if we can get it to work over here. There we go. What's going to happen is it is so unstable, it's now going to split itself in half, and that is going to give us 2 3-carbon molecules called G3P. They have 1 phosphate, so they're still a little unstable, but not really all that unstable. Now, it's important to note that for the rest of this slideshow, we're only going to focus on one branch here, not the other. So we'll just look at this side right here, and we're going to follow down the line. But remember, it happens on both sides, so everything we're going to talk about in stage 3 actually happens twice. I'm going to go ahead and move these molecules to the side here like this. So the next step we're going to do is we are left with this. This is stage 2 again. We're left with this G3P, and here we are at the beginning. And maybe just to help you see what's happening again, I'm going to put the line tool right there. What we're going to do with this G3P is we are now going to add another phosphate, because that seems to be the theme here. We're going to destabilize it. It It's kind of like if we had already destabilized it and the person fell over from a stack of books. As soon as they get back up, we're going to destabilize them even further. We're going to do it a little differently this time. Not sure why the scribble tool wasn't working quite there, but to do it this time, we could use another ATP and add a phosphate, but the problem is we wouldn't really be getting any energy if we did it this way. Because, you know, if we keep spending ATP, we're never going to make ATP. So what's going to happen in the stage 3 part of glycolysis is we are going to do a redox reaction. We have electrons on this sugar up here, and we're going to strip the electrons. We're going to do a redox reaction. We're going to bring in a oxidizing agent here called NAD+, and what it's going to do is it's going to strip the electrons off of this carbon and give it to NADH. Actually, it just converts itself. It doesn't really give it to anything. What we're going to do is we're going to strip the electrons off of the sugar, and now NADH is reduced and carrying energy. That means this molecule here is now, this molecule down here is now oxidized, and this molecule is now reduced. So we've actually lost energy in our sugar because we gave it to NADH. And by doing that, we are able to replace that energy with a phosphate. And that's where this phosphate comes in here. So we did the exact same thing we did in the first step, where we are adding a phosphate, but we didn't use an ATP. Instead, we used oxidation-reduction reactions to do this. So we stripped off the electron energy, and by losing energy, we were able to replace that vacuum and add a phosphate to the end there. Okay? So if you're following me through it so far, I'll go before we do the last phase. We started with a 6-carbon sugar. It was full of energy. We added phosphates to the end of it, but we had to sacrifice 2 ATPs to do this, and this caused it to break in half like this. Now, by this happening, we were now left with a G3P on both sides. We're just going to look at the left branch here, and what we're going to do is add yet another phosphate to it. It just can't catch a break, but we're going to do it by oxidizing the sugars, and that will mean give the electrons and reducing NADH. And that brings us to the very last phase. Now we're left with this 3-carbon molecule called PEP, and what we're going to do with this is we're going to, you guessed it, we are going to get those electrons off of there, and now we'll have our ATPs. Okay, so I'm going to draw an arrow down to here. So it looks like this might be the reason I can't draw an arrow, and I'm not sure why that's happening. So think about how could we make ATP from this, and the answer is we're going to bring up an ADP molecule with 2 phosphates, and we're going to give that other phosphate and make ATP. We're going to do that twice, just on this one pathway here. And by doing it twice, you can see that, well, we've now gained 2 ATP over here, and at the very end of glycolysis, we end up with 2 ATPs and a pyruvate. That is what happens. So we gained ATP, and we end up with a pyruvate. However, do you remember in stage 2 that this happens twice? So we only looked on this one branch, but it happens twice. So everything that happens here actually, if I can, move this over real quick. Not sure why it's being so annoying and not letting me copy it. Everything that happens here actually happened twice. And so if I can just move this over for you to see, what we really have ended up with at the end of glycolysis is we've ended up with 2 pyruvates, which have low energy compared to glucose. They've been oxidized. So we end up with 2 pyruvates, but we end up with 4 ATPs. However, we had to sacrifice 2 ATPs in the very beginning stage, and that means because we had to spend 2 ATP to make 4, we really gained only 2. So what is the starting substrates and the end products? We started with glucose, we ended with pyruvate. Okay, actually I'll just write this in here. We started with glucose and we ended with pyruvate. Okay, where does glycolysis occur in the cell? It occurs in the cytosol. Or you could say cytoplasm. How many pyruvates are made? And the answer is 2. Okay. And they both have 3 carbons. That's where our carbons went from the sugars. In total, how many NADHs are made? 2. Remember, we made an NADH here, but we did it twice, so it really happened over there too. And the last one here, in total, how many ATPs were made? Well, we made 4, but since we had to spend 2, we made a total of 2 net ATPs. There's your answers. Okay, so I hope this helped you a little bit. I know it is a lot to cover glycolysis, but if you can understand the flow of this and spend your time, it really is about that simple. It just takes a little bit of time to go through this. All right, have a wonderful day.